Hey, it's me, Steve, and as the title implies, I am going to apply Kepler and Newton to show you some kind of cool things you can do with those equations and how you can figure stuff out. But before I get into that, what I'm going to need to do is I'm going to need to explain, how do I put this, planetary motions. Kepler and Newton discovered these things in the 17th century, and it's not really difficult to comprehend this stuff. Checkbook math is not good enough. When I say checkbook math, I mean addition, subtraction, multiplication, division. It's more complex than that, but it's not impossible to understand. And once you take that math, you can cross check it with other results in order to see if you can reproduce someone else's results. And in science, that's important, reproducibility. And I'm going to do a little bit of that here. I'm also going to link to another video below where I did this for the Earth and Moon system, which I'm also going to play with here a little bit and kind of show you something cool. But before I get into that, I need to show you how one planetary body orbits another planetary body, or another body. It doesn't matter really what it is, as long as it's something orbiting something else in space. So let's get to it. Okay, this is just a diagram I drew showing how a very large massive body, which is the yellow circle in the middle, dominates, and the other minor bodies, the green, the gray, and the brown circle, orbit that big yellow one. This isn't a to-scale imitation mock-up of anything in particular. It's to illustrate a point. All right? And I'll refer to them as yellow, green, gray, and brown. Now, watch what happens as they orbit one another. Okay, did you see that? All right. Now, the thing to remember here is, and then I'll do it one more time, is that something orbiting a large body that's closer than something else, like in this case the green is the closest, the green not only has a shorter orbital period because its orbit is smaller, it actually has to move faster in that orbit around the yellow circle in order to maintain that orbit. That's how gravity works. It dissipates with distance. It's intense near a large object, in this case the yellow circle, and dissipates as you move out. And then the gray object, the middle object, moves slower than the green, but faster than the brown. And the brown object, being the furthest from the yellow circle, actually moves the slowest in its orbit. Now, just let you look at that one more time. Now, I hope you saw it there. And now I'm going to get into the meat of this. Okay, here we go. What I'm showing you right here, just really quick, and the website I pulled this from is at the very top. This is an Earth fact sheet given by NASA. All right, they have this for all the planets and the moon. I copied and pasted directly what they had, so no one has any excuse to sit there and say that this stuff isn't publicly available for free because I didn't pay a dime for it. All right, the website's right up there. All right, so here we go. All right, Kepler's third law of planetary motion can be mathematically written as p squared equals a cubed. P equals the period of the planet, and the a equals the semi-major axis of the orbit. All right, in astronomical units, and the p in years. This is what Kepler stumbled upon. All right, he noticed that if you square a planet's period in Earth years and cube its distance in the semi-major axis in astronomical units, the two numbers equal one another. All right, he just happened to stumble upon this. He didn't know why. Well, Newton came along and defined it better, and that's the Newton's version of Kepler's third law here, and that equals a constant. And what that constant is for our solar system, because we use Earth and the sun is the constant is 1, and the reason why it's 1 is because The sun is one solar mass. And even with all the other stuff in our solar system, even with that big daddy Jupiter, the sun is still 99% the mass of our solar system. So Newton's equation can be generically expressed as the capital M plus the small m is supposed to be the mass of the large object and the mass of the small object. In the case of the sun and the earth, or the sun and Jupiter, and the sun of anything, that's just equal to one solar mass. So it's just g, the gravitational constant, multiplied by mass. Now, where capital M plus small m comes into play is when you're using things that, like something relatively large to the celestial object that it's orbiting, it comes into play, like the Earth-Moon system. Off the top of my head, I think the Moon is 1.2%-ish the mass of the Earth. That's significant, all right? So that's when you need to compensate. You need to take both masses into account, okay? And here's some other definitions here. I put seconds in a year based on a 365.2422 day year. That's from NASA. And there it is in seconds. That's at 31,556,926.08 seconds. That's an exact number. Everything on here, other than the calculations that I perform myself, all this stuff you're going to see is from NASA unless it says otherwise. Like you'll see Wikipedia down below. And there's one astronomical unit in kilometers. There's 1 kilometer and how many feet that equals. And there's how Wikipedia defines 1 meter and how Wikipedia defines 1 second. All right. Now, at the very end of this video, I'm going to show you the paperwork I used to figure out these calculations so you can see them in general. And if you notice anything, any stupid little minor error with my calculations, please let me know. That's fine. But everything seems to have worked out. So there may be some loss in translation from my paperwork to writing to transferring it digitally here. But other than that, the math worked out just fine. All right, so using Kepler's third law, this is basically what he noticed. Okay, so I took 3 planets. I took Venus, Terra, which is Earth, and Mars. All right, and I translated the semi-major axis into astronomical units and the periods into Earth years. Okay, and then I included their mass in Earth masses. That's the m subscript e, and then their average orbital velocity. And if you notice, Venus is closer to the Sun than Earth, and Earth is closer to the Sun and Mars. And look at their orbital velocities. Venus is the fastest here, and Mars is the slowest. All right? That goes back to what I just showed you before I started talking about Kepler's third law here. All right? So what the red arrows do is I basically, like, we'll just use Venus here because I'm going to go deeper into Venus here. As you can see, the one red arrow goes from A equals 0.723332 astronomical units. All right, you take that, you square that, that's equal to 0.37845394442. Now you take the square root of that, and that gives you the period. All right, that's what I calculated. And then I did the vice versa for the top equation with Venus. All right, and as you can see, the lowercase a and the capital P near the yellow Venus there, that is NASA's data. And as you can see, my calculations aren't far off. So Kepler's third law works. And for Earth, it's real simple because everything equals 1. And so I did it for Mars as another check. And as you can see, it's a similar manner to Venus, just the numbers are different. And you can see there that my numbers are really close to NASA's, which are on the left. My numbers are on the far right. My calculations are in the middle. Okay, so I said I was going to go a little deeper into Venus. I could have done this for I could have done this for Venus, Mars, Earth. I could have done it for Mercury, Jupiter, Saturn, Uranus, Neptune. It doesn't matter. Even Pluto, I could have done it for Sirius the asteroid. It doesn't matter. All right, so I'm going to check the orbital velocity that NASA gives. That's the number in red here. So I have to, first I have to get the circumference of the Venusian orbit around the Sun. All right, and I'm using the semi-major axis of that lowercase a. All right, so you see c equals 2 pi r, which is equal to the circumference of a circle. That equation doesn't change. Here I have pi, and 2 pi. I put those values there because I'm going to use them again later, but I'm going to use those exact same numbers to those decimal places. So for future reference, that's the numbers I'm using. All right. RV is equal to the Venusian circumference of its orbit using the semi-major axis. All right. What I have, if you see me cross out something, I just wanted to show you how many decimal places I carried it to, and then from that point on, any further equations, I drop what's been crossed out. But I just want you to see that I carried it further than that. So we get the Venusian circumference of its orbit around the sun at 680,834,669.7 kilometers. Okay, so we need to figure out how many seconds in a Venusian year. All right, so we just take the number of seconds in a year and multiply that by how long it takes Venus to orbit the sun, and we get 19,413,757 seconds and some change. Now we calculate the orbital velocity, which is the circumference, which is c, that hasn't changed. I tried to keep my units, not my units, but my algebraic symbols consistent. So c is always going to equal circumference. Divided by SV, which is explained right above that, which is equal to kilometers per second. All right, there's the raw numbers, and I got basically 35.07 kilometers per second as an orbital velocity of Venus. Now, NASA gives it as 35.02. So here is the error calculation from my number in yellow to NASA's in red, and I'm off by 0.14%. So that works. See, that's how you cross-check things. Okay? If you want to know if NASA's putting out a bullshit number, this is how you check it. You don't just sit there and say, NASA lies, because that's not evidence. That's something you put on a bumper sticker. And the only people that swallow that crap are politicians and children. All right? So this is how you prove something works or doesn't work. And I got a pretty good match. I mean, that's almost dead on. You know, so now I'm going to take Kepler's third law and use it, and using Newton's interpretation of that law, a more detailed one, to calculate the lunar orbits in the terra-lunar system, Luna being the moon. So you've seen this equation before. This t squared is equal to 4 pi squared times the radius cubed over the gravitational constant times the mass of Terra and Luna put together. And these are the actual breakdowns. I've done this in another video before. I'll link it below. But I've calculated those myself. So, except for the gravitational constant, that's NASA's official one. So, I've said I think they might actually carry it one more decimal place, or one more place. I think it's 6.6744 is the official one. But that's the one I used in my calculations, is the one on the screen here. So this explains how in a previous video I calculated the orbital velocity of the moon at its present distance from the moon, which is 384,400 kilometers. That's a semi-major axis. I calculated that at 1.023 kilometers per second. NASA gives a value at 1.022 kilometers per second, or 1.02 if you want to round, knock off an extra decimal. So I was off literally by 1 meter. So I knew that worked in that video. But now let's have some fun. This is where the fun's going to come in. What if Luna at its present mass were closer or further away than it is today? Now, see, you can't just use Kepler here, because the moon is significantly large compared to the Earth, where you need to use Newton to figure this out. So I decided I was going to have some fun. All right? Okay. So what would the orbital velocity be if the moon was 5,000 kilometers from the Earth? Now, obviously the moon can never be that close, because the equation works as if all the mass of Earth were like the density of a neutron star, and then Earth would be, what is it, like 140 meters across, I believe. I forget the exact number, or 450 feet. I remember that for sure. So, however that translates into meters. So, obviously, the moon could never be, because that's less. That 5,000 kilometers is less than the diameter of the Earth, or even the radius of the Earth. But it's just fun to play with this because it's going to show you something, all right? And then I did it for 25,000 kilometers, 100,000 kilometers, 250,000 kilometers, 500,000 kilometers. And my goal was to generate a graph to show you something. And eventually I ended up running the calculations for more points to get more points on the graph, because I did a video a long time ago that talked about the relevance of data points, and the more data points you have, the more reliable your interpretation is. You like 2 data points is never a pattern. All right, I won't. I mean, you need more than that, and I end up running it for 17, which you're going to see here in a minute, and it forms this awesome curve, which I'll explain. But first, I'm just going to run you through what if the moon was at 25,000 kilometers from Earth, from the center of the Earth. What would the moon's orbital velocity be? Well, we need to turn it into meters, so we get 25 million meters. We're still using the equation on top. This is the math for it, okay? That 39.587415 is 4 pi r squared. That's what that is. And then there's the meters. You need to cube that. And there's our GM at the bottom, which I've calculated in that other video I already explained. And once we do this, we get this relatively large number. All right, 1,532,652,745.65. So what is that? Well, that is not the amount of time that it would take the moon at 25,000 kilometers to orbit, because that's a square. We need to take the square root of that, all right, which is kind of like Kepler's p squared, except here it's a t squared, all right? So we get 39,149.109 seconds. That's how many seconds it would take the moon at its present mass to orbit the Earth once at 25,000 kilometers. And here I broke it down into hours for you, and minutes and seconds. All right. When I ran the equations, I only used seconds because that's all I needed. But here it just gives you a more detailed, so you can form a concept in your mind of how short of a period that would be. All right. Now we need to get the circumference to get the orbital velocity. There's the equation there. It's the same equation for every circumference of finding an orbit using the semi-major axis. And the semi-major axis in all these hypothetical calculations I'm doing, the eccentricity is assumed to be circular or 0. All right, and I covered that in a different video. I'm not going to go into that here. So our orbital velocity works out to be 4.02 kilometers per second. All right. If the moon were 25,000 kilometers away, the orbital velocity would be 4.02 kilometers per second. Okay, and I did that for all those other examples that I showed you as well. So there's the 25,000 in the yellow highlight with the red box. And there's the values for the other ones that I showed you a few slides ago. Now, in order to get the graph to show more detail, I had to go back and do it for other distances. So I did it at 500 kilometers, 1,000, 2,000. Obviously, that wouldn't be possible for the moon to orbit inside the Earth. So, but that's just that's just what it would be if if all the mass was just condensed as tightly as it could be. All right, and then we get into more realistic things. 10,000 kilometers, 18, 25,000, 33,000, and so on and so on. I'm not going to beat this, but those are the numbers I got. So I went and I graphed them, all right? This is the graph I got. And as you can see here, The title's Terra Lunar Gravity Well, and I'm going to explain why that is in a second. And even here I put the equatorial radius of the Earth in kilometers, just to show you where this becomes significant, because obviously the moon can't orbit less than that. But this shows you a nice logarithmic graph. What it shows you, the point of me doing this was to show you that if the moon were closer to the Earth, it would have to orbit much faster in order to maintain that orbit. All right? And as it gets further out, it doesn't need to go as fast. Okay? That was the point of this. So it's to show you that, you know, a orbiting body's orbital velocity it doesn't just take less time if it's closer to the body because the orbit's smaller. It also has to move physically faster in its orbit. All right. Now you have like the ISS, the International Space Station, that orbits the Earth. I believe it's in an hour and a half or something like that. Now it's, you know, when you run the equations for that, well, the mass of the Earth is essentially 100% of the mass. It's not like the Earth and Moon where you have to take the Moon into account. You don't have to take the mass of the ISS into account. So it's not going to need to move as quickly as the Moon would if the Moon were at the same orbital distance from the Earth. All right. So, but that's just to show you graphically how that looks. And as for the gravity well thing, well, here's two slides I picked. Here's the websites. Because Newton, although he defined gravity and understood it to a degree, it was still viewed as a force. You know, a planet was in orbit because centrifugal force was trying to kick it out, and gravity was the force pulling it in. You know, kind of like, you know, a string on a, you know, you have a stick and then you have a string tied to it and a ball tied at the other end and you're spinning it around. Gravity would be the stick and the centrifugal force would be the ball was trying to go off. But the string would be the gravitational force keeping it circling around the stick. Well, Einstein comes along and totally smashes everyone's conception of space-time. Gravity, according to Einstein, this is not going to be a relativity talk. I'm not going to do that here. But I'm just going to say this. Gravity, according to Einstein, is not a force. Okay? It's an object's, like the moon orbits the Earth, not because of centrifugal, a tug of war between centrifugal force and the force of gravity. The moon orbits the Earth, and its natural linear tendency in warped space-time. Now, Einstein realized space and time are the same thing. All right, that's why we call it space-time. All right, and there are videos out there that demonstrate this point very well. So, the moon is in orbit around the Earth. It's just moving around, and the warping of space-time due to gravity is what keeps it in orbit. I hope I explained that. Clearly. Like I said, this is not a relativity lesson. I just wanted to show you why I had gravity well on that graph. So, I think that concludes that. That's it. And I hope you learned something. Feel free to leave any comments. And if you have any serious questions, I will entertain them. Just real quickly, as promised, here are my handwritten calculations for everything I just showed you in the video. Alright. These are the nicer, neater ones. When I started doing those other points, I kind of summarized the math a little quicker. But trying to get through this as fast as I can here for you. If you need to see anything else in detail, feel free to zoom in. Here's the quicker calculations for the other distances I ended up doing after I did those main ones you saw on the data points that were highlighted in yellow. Oh, and this one has, there we go. So that does conclude the video, and Thank you for watching. And seriously, I hope you learned something.